Hello and welcome to another lesson of Math 1314 College Algebra. Today we will be discussing Section 2.5 Quadratic Equations. In this lesson we will discuss solving quadratic equations by a number of ways. We will solve them by factoring, using the square root property, using the completing the square technique, and then finally using the quadratic formula. Now, the very beginning is factoring. So if you have trouble with factoring, be sure to go back to the section on factoring polynomials to get your skills honed up so you'll be ready for solving quadratic equations. Let's start with solving quadratic equations by factoring. To begin with solving quadratics by factoring, we first need to define the zero product property and quadratic equations. So first, the definition of the zero product property. The zero product property says that if we have the product of two numbers or algebraic expressions equal to zero, then either A has to be zero or B has to be zero, or both. The only way we get the product of two things equal to zero is if one of those things is equal to zero. Now let's define a quadratic equation. A quadratic equation is an equation containing a second-degree polynomial. For example, ax squared plus bx plus c equal to 0 is a quadratic equation where a, b, and c are real numbers. And if a is not equal to 0, this equation is in standard form. So what we have is an equation, or an algebraic expression, ax squared plus bx plus c equal to 0. If we were able to factor that into the product of two factors equal to 0, then we could set each factor to 0 and solve for x. So that's what we want to be able to do in solving quadratics by factoring. Let's try an example. Let's factor and solve the quadratic equation x squared minus 5x minus 6 equal to 0. So how would we factor this expression on the left-hand side? Well, we need to look for factors of -6. And then we need to look at their sums. Well, we know that we have 1 and -6. We have -1 and 6. We have 2 and -3, and -2 and 3. Let's see what those sums are. 1 plus a -6 is -5. -1 plus 6 is +5. 2 plus a -3 is -1. And -2 plus 3 is 1. So which pair of factors gives us the middle term, -5? Well, it's 1 and -6. So we can rewrite this expression on the left-hand side as x plus 1, x minus 6 is equal to 0. And we're factoring this expression here. Oops. That's how we get there. We factor that. Okay, so what we can do now is use the zero product property to figure out the two solutions. So set each factor equal to 0. So x plus 1 is equal to 0, or x minus 6 is equal to 0. So now we have two equations, two linear equations that we can solve for x. We'll start with the first one on the left. We can subtract 1 from both sides, so x is equal to -1. or we can add 6 to both sides of the second equation, and we get x is equal to 6. So our solutions are the two solutions to the equation are x equal -1 and x equal to 6. As a solution set, you would write that as the set containing -1 and 6. Let's try another example. In this example, we want to factor and solve the quadratic equation x squared minus 4x minus 21. So again, we have a leading coefficient of 1, and we need to find the factors of -21 and the sums of those factors. What are the factors of -21? Well, there's 1 and -21, -1 and 21, 3 and -7, and -3 and 7. So the sum of 1 and -21 is -20. Sum of -1 and 21 is +20. The sum of 3 and -7 is -4, and the sum of -3 and 7 is +4. So we want to get -4, so our factors are 3 and -7. So that equation should be equal to 0. So we can factor x squared minus 4x minus 21 as x plus 3 times x minus 7 equal to 0. Set both factors equal to 0. X plus 3 equals 0. Rewrite that x. Or x minus 7 is equal to 0. Subtract 3 from both sides. X is equal to -3. Or add 7 to both sides of the other equation. X equals 7. So the solutions to the equation are x equals -3 and x equals 7. The solution set is the set containing -3 and 7. So how would we generalize solving getting the solutions, solving a quadratic equation with a leading coefficient of 1? Steps for solving a quadratic equation. Quadratic equation that can be factored. And we'll say this is with the leading coefficient of 1. The first step is to find two numbers whose product is C, the constant term, and whose sum is B. Then write out the two factors x plus k or x minus k, where k is one of the numbers found in step 1. In the previous example, the numbers found were, what were they? -3 and 3 and 7. 3 and -7. So we write that as x plus 3, x minus 7. And then finally, solve using the zero product property by setting each factor equal to 0 and solving for the variable. So what happens when we need to solve a quadratic equation when the leading coefficient is not 1? Well, the answer is the same, that we try to factor it. If we can factor it, then we can solve it in the same way using the zero product property. Let's try an example. Solve using factoring by grouping. (12x² plus 11x plus 2 equals 0. So what do we want to do? Well, we need to look at the factors of a times c. What is a times c? Well, that's 12 times 2, or 24. The factors of 24, and we want the sum of those to equal 11. Well, we have 1 and 24, 2 and 12, 3 and 8, 4 and 6. Are there any pairs that sum to 11? Well, 1 and 24 is 25, 2 and 12 is 14, 3 and 8 is 11, and 4 and 6 is 10. So we want the pair that includes 3 and 8. So we want to rewrite this equation as 12x plus 3x plus 8x plus 2 is equal to 0. Again, we want to split that middle term into separate factors so we can factor by grouping. So let's consider the first two terms, and that should be 12x². We want to factor out a 3x, and that leaves us with 4x plus 1 plus, and then in the second we can factor out a 2, which gives us 4x plus 1 equal to 0. Now we have a common factor of 4x plus 1, and the second is 3x plus 2 equal to 0. Now we can solve that same thing as we did when the leading coefficient is 1, is we can use the zero product property. We set 4x plus 1 equal to 0, or 3x plus 2 equal to 0. We can subtract 1 from both sides. We have 4x is equal to negative 1. I'll rewrite that on the next line here. Divide by 4. X's cancel, or the 4's cancel. X is equal to negative 1/4. And then on the other side, subtract 2 from both sides. We have 3x is equal to negative 2. Divide both sides by 3. 3's cancel. We have x is equal to negative 2/3. So, our solutions to the equation are x equal to negative 1/4 and x equal to negative 2/3. The solution set would be negative 1/4, comma, negative 2/3. So again, the leading coefficient was not 1. We still factored using the tools that we have, and we were able to come to a solution using the zero product property, using factoring by grouping. Let's consider another concept. In this example, we want to solve by factoring x cubed plus 11x squared plus 10x equal to 0. Now you may be asking yourselves, why are we trying to solve a third degree polynomial when we're discussing quadratics? Well, remember, when you factor an expression, the first thing you want to try is factoring out a greatest common factor. And it turns out that in this case, we can factor out an x. And that lets us rewrite this as x times x squared plus 11x plus 10 is equal to 0. Now, we have a quadratic expression inside the parentheses, which we can then factor. We can see if it factors. What are the factors of 10 that sum to get 11? Let's see if that works. We have 1 and 11. Not 1 and 11, 1 and 10, 2 and 5. And those are our factors. The sum of 1 and 10 is 11. The sum of 2 and 5 is 7. So the factors we want to choose are 1 and 10. So we can rewrite this as x times x plus 1, x plus 10 equal to 0. Now we have 3 factors that we can check to see when they equal 0. Well, the first, if x is equal to 0, that causes it to be 0. If x plus 1 is equal to 0, we can subtract 1 from both sides. X is equal to negative 1. So I'll box those in. And then x plus 10 equal to 0. Subtract 10 from both sides, and x is equal to negative 10. So what we just did is we solved a third degree polynomial using factoring by simplifying it to be the product of x and a quadratic expression. So our solutions are x equals 0, x equal negative 1, and x equal negative 10. As a solution set, that would be negative 10, negative 1, and 0. Let's now consider the square root property. If we have the x squared term isolated in a quadratic equation, the square root property says that if x squared is equal to some non-zero real number k, then x must be equal to plus or minus the square root of k. Let's try an example. We're asked here to solve the quadratic equation x squared is equal to 8. So the square root property says that if we have x squared by itself equal to some non-zero real number, then we can take the square root of both sides and find the solutions. So if we take the square root of both sides, we have x is equal to the plus or minus, positive or negative, square root of 8, which we can simplify as plus or minus the square root of 2 times 4, which is equal to plus or minus the square root of 2 times the square root of 4, or plus or minus 2 times the square root of 2. So our solutions are x is equal to 2 times the square root of 2, and x is equal to the negative 2 times the square root of 2. Solution set being negative 2 times the square root of 2 and 2 times the square root of 2. Let's try a little more complicated example. Solve the quadratic using the square root property. We have 3 times the quantity of x minus 4 squared equal to 15. Well, our first step is to divide both sides by 3. The 3's cancel on the left side. We have x minus 4 quantity squared is equal to 5. And what we have is something squared is equal to 5. So what we can do is take the square root of both sides, and what we get is x minus 4 is equal to plus or minus the square root of 5. We can add 4 to both sides of this, and we get x is equal to 4 plus or minus the square root of 5. Now be very careful when you take the square root of both sides, is that you have to put the plus or minus with what is left. We're able to do this step, and I want to pull up we're able to do this part, the x minus 4, and add both sides because what we started with was a quantity squared. So that gets us down to x equal 4 plus or minus the square root of 5. So our solution set in this case would be 4 plus the square root of 5 and 4 minus the square root of 5. So it's not always the case that we can factor a quadratic equation. Not all expressions can be factored or solved in their original form using the square root property. So in these cases, sometimes we will use the method for solving a quadratic known as completing the square. When we use this method, we add or subtract terms to both sides of the equation until we have a perfect square trinomial on one side of the equal sign. Then we're able to use the square root property to get the plus or minus thing that we had in the last example. So let's use an example. We have x squared minus 6x minus 13 is equal to 0. Okay. We can first check to see if this can be factored. What are the factors of negative 13 that sum to give us negative 6? Well, let's check. Factors of negative 13 are 1 and negative 13, and negative 1 and 13. The sum of those, the sum of 1 and negative 13 is negative 12, and the sum of negative 1 and 13 is 12. So we cannot factor this quadratic. So we want to complete the square. So first, to complete the square, what do? Well, we want to move, not add, move the constant to the right side of the equal sign. So x squared minus 6x minus 13 equals 0. We can add 13 to both sides, and we get x squared minus 6x is equal to 13. Our second step is to multiply the b term by 1/2 and then to square it. So what does that mean? That's -6 times 1/2 squared. The b is -6. That's the coefficient in front of x, just x, the linear term. -6 times 1/2 is equal to -3 squared, which is 9. So now what we want to do is add that 1/2 b squared to both sides of our equation. One half b squared to both sides of the equation. And so we'll take the equation again. X squared minus 6x plus 9 is equal to 13 plus 9. Again, we've added 9 to both sides. And the resulting equation is x squared minus 6x plus 9 is equal to 13 plus 9, which is 24. Sorry, 22. And then the left-hand side of the equation can be factored. It's a perfect square as x minus 3 squared is equal to 22. So we can take the square root of both sides, and we get x minus 3. So we'll take the square root of both sides is equal to plus or minus the square root of 22. Again, remember, when you take the square root of the right-hand side, you have to have the plus or minus. So we have x minus 3 is equal to plus or minus the square root of 22. We can add 3 to both sides, and we get x is equal to 3 plus or minus the square root of 22. So our solution set is 3 plus the square root of 22, 3 minus the square root of 22. And this works in general for solving quadratics. You can always complete the square, even in cases where it doesn't factor. You can always do this, which will eventually lead us to being able to use the quadratic formula to solve quadratic equations. And we can actually derive the quadratic formula using the completing the square method, which we will do now. So in general, a quadratic can be written as ax squared plus bx plus c equal to 0. And we assume, for this case, that a is not equal to 0. Then we can complete the square for this general quadratic equation which could represent any quadratic equation, as follows. So we first want to rewrite the equation. We want to move the constant to the right-hand side, so we get ax squared plus bx is equal to negative c. Then what we want to do is we want to divide through on every term by a, to get x squared plus b over a times x is equal to negative c over a. So now what we can do is we can find half of the middle term and square it. So b over a, not b over 2, times 1/2, and square that. We get b squared over 4a squared. So what we wanted, that's our middle term. That's how we complete the square. So what we can do is we can add b squared plus b squared over 4a squared to both sides. So x squared plus b over ax plus b squared over 4a squared is equal to negative c over a plus b squared over 4a squared. So now we have a perfect square on the left side. And what is that perfect square? Well, that perfect square, if we were to rewrite it, is x plus b over 2a, quantity squared, is equal to b squared minus 4ac over 4a squared. Writing this as a single fraction. Okay? And then what we can do is take the square root of both sides, and we get x plus b over 2a is equal to the plus or minus the square root of b squared minus 4ac all over 4a squared, which we can then rewrite as x plus b over 2a is equal to plus or minus the square root of b squared minus 4ac all over 2a. So what can we do now? We'll subtract b over 2a from both sides, and x is equal to negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. So we have a common denominator there, so x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So that is the solution for any quadratic. That is the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Now that's how you derive the formula. You probably will never need to derive the formula, but that's how you do it. So let's write the definition of the quadratic formula. Written in standard form, ax squared plus bx plus c equal to 0. Any quadratic equation can be solved using the quadratic formula x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, where a, b, and c are real numbers and a is not 0. So again, we've defined it, the quadratic formula. If you can't tell how important this is, that it's been derived and then defined, this is very important for being able to solve quadratic equations. Next, we will discuss how to solve quadratic equations using the quadratic formula. If we're given a quadratic equation, how do we solve it using the quadratic formula? Well, our first step is to verify and make certain that the equation is in standard form. Ax squared plus bx plus c is equal to 0. Then we want to note the values of the coefficients a, b, and c. Then we want to substitute a, b, and c into the formula. Something to note, it may be helpful to use parentheses around numerical values you substitute. And then finally, we want to calculate and solve. Let's use these steps now to solve a quadratic equation. The first example we want to do is solve using the quadratic formula 9x squared plus 3x minus 2 is equal to 0. So what do? We first want to make sure that it's in standard form, which is ax squared plus bx plus c equal to 0. In other words, we want the left-hand side to be equal to 0, which we have. We want to make note of the values of the coefficients of the terms. So a in this case is 9, b is equal to 3, and c is equal to -2. So we will now carefully substitute those values into the quadratic formula. Let's rewrite the quadratic formula. X is equal to what? -b plus or minus the square root of b squared minus 4ac all over 2a. So let's substitute. So we have -3 plus or minus the square root of 3 squared minus 4 times 9 times -2 all over 2 times 9. Okay, let's start in the radical. 3 squared is 9. So let's copy it down. -3 plus or minus the square root of 9 minus 4 times 9 times -2. 4 times 9 is 36 times -2 is 72. So 9 plus 72 all over 2 times 9. So what we end up having is -3 plus or minus the square root 9 plus 72 is 81 over 2 times 9, which is 18. So we have -3 plus or minus the square root of 81 is 9 over 18, which is -3 plus 9 over 18, or -3 minus 9 over 18. So x is equal to -3 plus 9 is 6 over 18, or x is equal to -3 minus 9, which is -12 over 18. Are we finished? Well, we can simplify these a little bit further. X is equal to 1/3, or x is equal to -2/3. So our solution set would be the set containing -2/3 and 1/3. So that's how you solve a quadratic equation using the quadratic formula. Now there's something significant about the part that goes underneath the radical, that b squared minus 4ac business. And that tells us what kind of solutions we will get and the number of solutions. You may notice that because we have a radical symbol, that we may end up with something that's negative under there. And so that leads us to the next discussion, and that's b squared minus 4ac. So the stuff underneath the radical symbol in the quadratic formula, b squared minus 4ac, is called the discriminant of the equation ax squared plus bx plus c equal to 0, which tells us whether solutions to that equation are real or complex, and how many solutions of each type to expect when we're solving. So let's build a table. Okay, I have the value of the discriminant and the results. It's not quite where I want it. Okay, and we'll bring out the handy dandy ruler so we make sure we have a good table. Have to have the pen open so it'll draw. Okay. out just a bit. Okay, gives us a good start. So what happens if b squared minus 4ac is equal to 0? Well, in that case, we have one rational solution, which is called a double solution. Okay? That takes care of one case. What happens when b squared minus 4ac is greater than 0 and is a perfect square? Well, then we get two rational solutions. Again, we'll bring our ruler out. Okay, that gives, we talked about when it's a perfect square and greater than 0. What happens when it's not less than 0? Greater than 0, not a perfect square. Then we get two irrational solutions. And we get irrational solutions because it's not a perfect square. And then the only case that we have left is when b squared minus 4ac is less than 0. And when that's less than 0, that means that the part of the solutions that is under the radical is negative. That means we get two complex solutions. Okay, we'll dress this table up nicely. And there you have it. Those are all of the possible values of the discriminant. This will determine the number of solutions you have and the type of solutions. Using the discriminant, let's do an example and find the number and type of solutions of the equation 3x squared minus 5x minus 2 equal to 0. So what we need to determine is the value of b squared minus 4ac. Well, our b in this case is negative 5 squared minus 4 times a is 3 times c is negative 2. Well, negative 5 squared is 25. We have negative 4 times 3 is negative 12 times negative 2 is 24. So we have 25 plus 24. 25 plus 24 is 49, not 42, 49. We know that 49 is a perfect square. So 49 is greater than 0, correct? 49 is greater than 0, so we're in one of these two cases. And it is a perfect square, so this is the case we're in. That means we have two rational solutions. So in this case, we can say, therefore, since b squared minus 4ac is equal to 49, there will be two rational solutions. The final concept of this section is one of the most famous formulas in all of math, the Pythagorean theorem, which says that the relationships between the lengths of the sides of a right triangle A, B, and C with A and B adjacent to the right angle and C the longest side, or the hypotenuse, then A squared plus B squared is equal to C squared. So if we're given a right triangle, see if I can draw that, the right angle in the corner there. If we have A, B, and C, those lengths can be represented by the formula A squared plus B squared is equal to C squared. So if we're trying to find the length of a missing side of a right triangle, then we end up having to use quadratic equations to solve for that. We end up having a square, something squared is equal to a number. So let's try and solve a right triangle problem where we know where leg A measures 4 units, leg B measures 3 units, and we need to find C, the hypotenuse. Okay. So we have a triangle, right triangle, whose lengths are 3, 4, and C, and we want to find what C is. Well, the Pythagorean theorem says that A squared plus B squared is equal to C squared, so 3 squared plus 4 squared is equal to C squared. Well, 3 squared is 9 and 4 squared is 16. 9 plus 16 is 25 is equal to C squared. We go back to using the square root property. We can take the square root of both sides. Now, normally, in every case that we've done, you've done the plus or minus on the square root of the number. But in this case, because we're dealing with a value in geometry and real space, it doesn't make sense to consider a measure that's negative. So C is equal to 5. So our triangle is one of the famous triangles whose lengths are 3, 4, and 5. That concludes all of the examples and concepts in section 2.5 for quadratic equations. If you have any questions, be sure to email me or come by my office hours and we'll get you set up. Good luck on the homework.